Okay, what I'd like to do now is I'd like to go ahead through the derivation for Bernoulli's equation, because we kind of just throw it out there and say, oh, well, you do some work, dot, 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 and there you go. So excuse my drawing. I'm going to go ahead and draw a picture of the tubes. So here I have the tube, and then it's going to go up to a smaller tube. I'm going to try to draw this the best I can with a mouse. Okay, and if I look at this piece, I will see that this piece is probably equivalent in my volume. Okay, so we're looking at a piece of the fluid that has the same volume. So in this case, V1 equals V2, and that's your volume. This is going to have a very slow speed. This is going to have a fast speed. Okay, that means that the pressure that is located here is going to be larger. So I'm going to call this P2, and I'll call this V. Actually, I'm going to call this P1. Let me replace that. Okay, so this is going to be V1, P1, and this is going to be the pressure here at P2, and this is going to be V2. And I know that P1 has a greater pressure than P2. Okay, so now what I'm going to do is I'm going to go ahead and calculate how much work needs to be done in order to move this fluid up. Since P2 is going to be greater than P1, what I'm actually going to do here is when I solve for the work done, I'm going to be making it negative F dot D. Okay, and I'm going to be using the magnitudes of these, because I know that this work done is going to be negative, non-conservative. Okay? So let's go ahead and look at the derivation. Work is equal to the final energy minus the initial energy. And again, remember, I'm putting the negative here explicitly because I know that my force dotted with my displacement is going to give me a negative number because it's energy that I have to put in to the system. Okay, it's non-conservative work. Okay, so what I'm going to do is I'm going to set my final minus my initial equal to delta PE plus delta KE. That gives me mgh final minus mgh initial plus 1/2 mv squared final minus 1/2 mv initial squared must equal the negative work done. We know that mass is equal to rho times volume, or the density times the volume, and I know that the volume is the same throughout the fluid because that's the section of the fluid that I chose. So I'm going to go ahead and replace m with rho v for all of them. The density in this case remains constant, but I did put rho 1s and rho 2s to indicate the location. But again, we're not looking at a compressible fluid. So we're assuming that the fluid in these problems is an incompressible fluid and that the density should remain constant. Okay, so here's our equation. Now let's look at work. Work is F dot D, and I know that the force here can be replaced with the pressure dotted times the cross-sectional area. That's the definition of pressure, is force per unit area. So if I look at the work being done, it's P2 minus P1 times A, and then I'm going to multiply that by the D, the distance traveled. I know that the area times the distance traveled is just my volume. Okay. Now I'm going to substitute this in to the previous equation, and now I'm going to go ahead and cancel out my volume off of all of the terms. They all have the same volume. Okay, and now what I'm going to do is I'm going to go ahead and combine like terms. So I'm going to go ahead and put all the 2's together and all the 1's together. And so here you end up with P2 is equal to the density times the acceleration due to gravity times the height at position 2. And that's plus 1/2 rho V2 squared. And that's equal to the pressure at position 1 times rho g h1 plus rho 1/2 rho 1 v1 squared. Okay, now these two things are equal, so you could say that they're equal to a constant, which is what the lecture notes use. But this really is what we use to find the values for instance, the speed or the pressure at position 2 versus position 1. You can use Bernoulli's equation, which comes from the work energy theorem.